Welcome to The Explainer. Today, we are getting into the kitchen to break down one of the most critical and, honestly, one of the most creative parts of machine learning, feature engineering. This is the secret sauce, the thing that can make or break an AI model. So let's just start with a really basic question. We've got these incredibly powerful AI models, right? So why can't we just, I don't know, dump a huge pile of raw data on them and expect magic? Well, the answer really gets to the core of what it means for a machine to learn anything at all. To really get this, let's use an analogy we're going to stick with. Imagine your data is a pantry full of raw ingredients, and your AI model, well, that's a world-class chef. Now, even the most brilliant chef in the world can't make a masterpiece if the ingredients aren't prepped. You've got to wash the vegetables, you have to fillet the fish, you have to measure out the spices. That prep work, that's everything. Okay, so let's talk about that pile of unprepared groceries. This is what we call the raw data problem, and it's the entire reason feature engineering even exists. Before any real learning can start, we have to turn all that raw potential into something refined, something usable. First things first, let's get on the same page. What even is a feature? Simply put, it's just one piece of information. Think of a spreadsheet. Each column, age, height, price, that's a feature. It's a single, measurable piece of the puzzle. And that right there leads us straight to our main event today, feature engineering. This is both an art and a science. It's the process of taking those raw columns and transforming them into features that actually help the model see the world clearly. It's about making the data speak the model's language, which is what unlocks that incredible performance we're all after. So our data chef, right? They've basically got two big jobs in the kitchen. Think of these as the two main techniques they use to prep the ingredients and make them just perfect for our AI model. Let's break those down. You can really boil it all down to two things. On the one hand, you've got feature transformation. This is all about changing your ingredients, maybe combining them to create something new and even better. And on the other hand, you have feature selection. This is about being picky, choosing only the best ingredients and throwing away the stuff you don't need. All right, let's get our hands dirty with that first job, transformation. This is where a lot of the creativity really happens. We're not just picking and choosing here. We are actively changing our ingredients to make them way, way better. So the first move we can make is something called feature construction. The big idea here is that sometimes the most important information isn't in your starting data. It's hidden in the relationships between your data points. Our job is to find those hidden relationships and make them a brand new explicit feature for the model to see. Check this out. Imagine a super simple dataset for predicting apartment prices. We have length and breadth. Now, a model could try to figure out how those two separate numbers relate to the price, but it's not exactly intuitive, is it? And boom, this is where the magic happens. We just do a simple multiplication, length times breadth, and we create a new, much more powerful feature, apartment area. All of a sudden, the model has something amazing to work with. The link between 600 square feet and a price of $250,000 is so much clearer and more direct for the model to learn from. Now, the flip side of this transformation coin is something called feature extraction. Okay, so if construction is about adding new features, extraction is usually about reducing them. It's kind of like a chef taking a super complex sauce with 20 ingredients and simmering it down and down and down until all that's left is the most concentrated, essential flavor. And you know, data scientists have some seriously powerful tools for this. The most famous is probably something called Principal Component Analysis, or PCA. Now, without getting way too technical, just imagine PCA looks at a bunch of features that are kind of related, like a person's height and weight. They often go up and down together, and it distills them into a smaller set of brand new features that are totally unrelated, but still capture most of the important information. It's like the ultimate sauce reduction algorithm. Okay, so that was transformation. Let's switch gears and talk about our chef's second big job, feature selection. This time, we're not creating anything new. We are simply making smart choices about what ingredients to keep and what to throw out, all based on that timeless principle that sometimes less really is more. So why is this so important? I mean, just look at this quote. In fields like biology, you can get data sets with 450,000 different features for every single data point. Can you imagine trying to teach a model with that? It's not just slow, it would be a computational nightmare, just full of noise. Selection isn't a nice to have, it's an absolute necessity. So when we're choosing our features, we're really fighting against two big enemies. The first is irrelevance, features that are just noise. A student's ID number has absolutely nothing to do with their weight. It's useless. The second enemy is redundancy, having two features that tell you basically the same thing. If you already know someone's age in years, also knowing their age in months probably isn't adding a whole lot of new insight. So the big question is, how does our chef actually do this? I mean, it's not just random guessing, right? Of course not. There are established methods that data scientists use to systematically find the absolute best group of features for the task at hand. Well, there's a pretty standard playbook for this, a kind of four-step process. First, you generate a bunch of different combinations of features. Then, you evaluate each of those combinations to see how good it is. You need a stopping point, a rule that says, okay, this is good enough. And finally, you validate your chosen set of features to make sure it actually works well. And when you get to that evaluation part, there are two main ways to go about it. The filter approach is kind of like a chef quickly sniffing an ingredient. It's a fast, statistical check for freshness. Then there's the wrapper approach. This one's more thorough. It's like making a tiny test batch of the recipe, using the actual AI model to score the features. It's a lot slower for sure, but it often gives you a much better result. Okay, let's take a step back and bring this all together. Why does any of this matter? I mean, why do data scientists spend a huge chunk of their time just on this prep work? Why is it so fundamental to machine learning? Well, it really comes down to three huge wins. First, good features mean your models are just plain faster and cheaper to build and run. Second, they lead to models that are more efficient and more accurate. And third, and this might be the most important part, the process forces us to get a much, much deeper understanding of our data and the problem we're actually trying to solve. And that leaves us with one last big question to chew on. Right now, feature engineering is a very human thing. It's this mix of expertise, intuition, and creativity. But as these AI models get more and more powerful, will they eventually learn to just do this for themselves? Will the data chef of the future still be a human? Or will the machine one day become the chef?